Now, when you build current in an inductor, starting from zero current, the inductor creates a magnetic field that fights the current that you're trying to develop. So it takes a little while to develop the current, and you have to do work to do that because the magnetic field gives you a voltage opposed to your increase in current. Okay, so you have to do work against that voltage. Well, how do we get energy in an inductor? Just from basic principles, voltage is what? What's the voltage in an inductor? Well, we answer L di dt. Okay? And voltage is energy per unit of charge. Okay? So current is the rate of change of charge, which is charge over time interval. So that if you multiply the energy per unit of charge by the charge per time interval, which is exactly what these units or these quantities suggest doing, you get energy per time interval, which I'll write the time interval as delta t, so energy over charge multiplied by charge over a delta t. Of course, we're thinking about a very tiny delta t. I could write that as a dt, so it's just an incremental time change in the clock time, an incremental time interval. But I'm going to write it with a delta. Energy per unit charge times charge over time interval gives you energy per time interval, doesn't it? Okay, well, energy per unit of charge is L di dt. That's your voltage. And your charge per unit of time is your current. And that's equal to what? It's equal to the change in energy per unit of time. Okay? It's equal to the delta energy over delta t if you wish, but in the limit it's a d energy over dt. Well, then if we integrate okay, I'm just going to talk about this formally because it goes too deep to talk about it in a more intuitive fashion. But if we have this with respect to t and the change in energy with respect to t, we can say, well, just the differential here is equal to the differential here. So Li di equals the differential of your energy. When we integrate the differential, well, we integrate the differential of energy, we get energy, and we integrate the differential of Li di, we get Li squared over 2. Now that's just a straightforward integral. You know, I comes out of the integral. Integral of I di is I squared over 2. So the energy is L times I squared over 2. Okay, well that's the energy stored in an inductor. And if the inductor releases, you know, if the current in the inductor is allowed to then come back to zero, you're going to get that much energy in your circuit. You're going to have to dissipate that much heat or whatever. Okay, well, that's it. That's the energy stored in an inductor. Now there are analogies between mechanical energy and the energy in an LC circuit. And even more general analogies between the mechanical and the circuitry, the situations you get with mechanics and circuits involving inductors, capacitors, and resistors. So we're going to talk about that next.